Welcome to the AI Research Roundup. I am Alex, and today is May 11th, 2025. We are looking at a fascinating research paper from Hugging Face's trending list, published just 4 days ago. ZeroSearch, Incentivize the search capability of LLMs without searching. This paper introduces ZeroSearch, a framework using reinforcement learning. That is a way AI learns from trial and error to boost LLM search skills without costly live search engines. It starts with supervised fine-tuning, essentially training an LLM to act like a search retriever, and then uses a curriculum-based rollout strategy, making simulated search tasks progressively harder. Okay, so this diagram really helps visualize how ZeroSearch works under the hood. It shows the training setup for 2 different reinforcement learning algorithms. Proximal policy optimization, or PPO, which is a popular technique that helps the AI learn new behavior steadily, and also grouped reward policy optimization, or GRPO. In both, a query enters the rollout module. Here, a simulation LLM and the policy model that we are training work together to produce an output. This output is then evaluated by reward and other models to refine the policy, all without needing a live search engine. Alright, building on how that rollout module functions, this table illustrates a template for the search simulation. It is essentially the instruction given to the simulation LLM, telling it to act like a search engine. Notice the keywords useful or noisy. These are used to control the quality of the documents generated for a query. The template also provides the question and its ground truth answer, which is the correct, verified answer for the question, helping the simulation LLM expand its knowledge. This careful prompt design is crucial for the simulation. Moving to the results, this table presents the main findings, comparing ZeroSearch against various other methods. We see performance across different question-answering benchmarks, like NQ and Trivia QA, which are single-hop question-answering tasks where the answer is usually found in one piece of text, and also multi-hop question-answering tasks such as Hotpot QA, which require combining information from multiple sources to find the answer. The scores here, often reflecting an exact match score, which measures if the model's output perfectly matches the correct answer, show ZeroSearch methods, especially when instruction-tuned, frequently achieving the highest results, highlighted in bold. This clearly demonstrates its effectiveness. Okay, to give us a visual on how the training itself progresses, these plots show the training reward curves. The first 2 plots, A and B, compare ZeroSearch with Search R1, a method using a real search engine on both a base llama model and an instruction-tuned llama model, which is a version specially trained to follow instructions. We see ZeroSearch's train reward, a score for how well it is learning, shows a generally more stable increase. Plot C then shows ZeroSearch's reward alongside interaction turns, likely the number of steps in its simulated search, demonstrating efficient learning within its curriculum. So, to further evaluate just how well these simulated search engines work, which is really the heart of ZeroSearch, this table compares different configurations. We see prompt-based simulations of various sizes, and then models that underwent supervised fine-tuning, or SFT, which, as we discussed, trains an LLM to specifically act like a search retriever. Looking at the average scores across these benchmarks, the larger supervised fine-tuning model, the 14 billion parameter one, actually performs on par with, and even slightly surpasses, Google Search. This really highlights the effectiveness of creating a high-quality simulated search environment. Beyond just performance, well, this next table gives us a clear picture of the cost implications. It compares the ZeroSearch approach, using those supervised fine-tuning models of various sizes, against using Google. For a similar number of queries in training time, the API cost, which is the expense for using an external service like a commercial search engine, is $0 for ZeroSearch, but nearly $600 for Google. Even when factoring in GPU costs for running the supervised fine-tuning models, the total cost for ZeroSearch remains dramatically lower. This really underscores the cost-effectiveness advantage. So, as we have seen, this ZeroSearch approach is not only highly effective, but also remarkably cost-efficient. What we have explored here is essentially a novel reinforcement learning framework, where AI learns by trial and error to boost LLM search skills without live search engines. It uses a curriculum-based rollout strategy, gradually increasing task difficulty, and also a technique called loss masking, which helps the model focus its learning on the most important signals. The key takeaway is its ability to match or even surpass real search engines, very cost-effectively. That is all for this AI Research Roundup. Thanks for tuning in.